Hello again, this is Mrs. Chirigno, and this is page 5 of the Algebra 1B Semester 2 exam review. This one will pick up with question number 22 and go through question number 25. So 22 says, a new car that costs $18,400 is predicted to depreciate at a rate of 12% per year. About how much will the car be worth in 5 years? I saw a lot of people in class trying to do this one with the compound interest formula, but there's no interest rate here. This is a depreciation problem, which means it's an exponential decay problem. So you're using this model, y equals ab to the power of x, where a is the amount you're starting with, b is your growth factor, and x is your time. So my starting value is that 18,400. Now the growth factor on this one is the trickiest part because it tells you that you depreciate at a rate of 12% per year. But remember that you don't really care about what you're losing. What you care about here is what you're keeping. So if you're losing 12% per year, you're keeping 88%. And really what I did there is I just did 100% minus 12 and got 88%. So my growth factor is 0.88, and then it'll be to the power of time, which is 5 years. So this is my setup, 18,400 times 0.88 to the power of 5, and then that can go straight into your calculator. Again, I recommend typing it in all in one shot so that you don't mess up order of operations. Make sure you're typing it with me to make sure you get the right answer. But I end up with $9,710.27. Remember, you're rounding to 2 decimal places. So my final value after 5 years, $9,710.27. Okay. Okay, question 23. Sketch a graph of one of these functions. That's that ab to the x that we've been talking about, where a is bigger than 0 and b is between 0 and 1. Well, let's think about this. Remember, a is your starting value. Your starting value is always bigger than 0. So really, this doesn't matter to you as far as making the graph. This is the important part, that b is between 0 and 1. So that's your growth factor. If your growth factor is between 0 and 1, and remember I told you in the last video that if b is less than 1, then that's decay. So that would be this situation here. b is between 0 and 1. That means I'm going to start out on the left here with a high value, and I'm going to lose value. Okay, so it's going to kind of swoop down this way. It'll look like this. Okay. Well, it's not a very smooth graph, but hopefully you get the idea. I'm just asking you for a sketch there anyway. What you want to watch out for, remember these graphs have that asymptote down the middle, so you never want your line to cross the x-axis, okay? So again, because the b was smaller than 1, I swoop downward as I move to the right. If b had been larger than 1, I would have started small and then swooped up to the right. So I would have started small and gotten big. That's the difference between the two types of graphs. Okay, let's take a look at 24. 24. The amount of a certain radioactive substance decreases continuously. Now this is a new formula here. That word continuously should stand out to you because we learned a separate formula for continuous growth, and that was the PERT formula. Okay, where P was your starting amount. E is just a mathematical constant. It's like 2.718 something something, but your calculator has an E button on it. And then R is the rate of growth or decay, and T is your time. Okay? So here, my starting amount, and this one, okay, this one's a little bit confusing because it's saying that I have 5,000 right now, and I want to know how much I had 3,200 years ago, 3,200 years in the past. So really, it's like I'm solving for that starting amount. But when we did these in class, we found it easiest if we pretended that 5,000 was our starting value. And then E just stays E, because remember that really represents just a number. My rate, now, first of all, this is 0.04%, but that's still a percentage. So to put it in my problem, I need to move that decimal twice to the left. So R really becomes 0.0004. Okay, be careful about that. Oh, didn't see it off to the right there. I'll say that again. That 0.04%, we want to move that decimal place 2 to the left, which makes it 0.0004. And since I'm decreasing, that's a negative. So negative 0.0004 in for R. So e to the power of negative times. And then remember, we said this is 3,200 years ago. So if we're treating 5,000 as our starting value, really it's like we want to turn the clock backwards 3,200 years. And we're going to do that by making our time negative. Okay, so in a practical sense, I know that doesn't make much sense, but mathematically that'll be accurate, as I just want to go back in time 3,200 years. Okay, this whole thing should be able to go into a calculator. I must say, though, that the calculator I have here at home does not have an E button on it. So what I'm going to recommend to you, and I apologize for that, I don't have a graphing calculator here at home with me this weekend. So this is going to go straight into your calculator. You can find that E to the power button up above the LN key on your calculator. So look for a button that looks like this, E to the power of X, and it's usually up above the LN key. But once you find that, you should be able to type that whole thing into your calculator, and then I will calculate the answer to that tomorrow and have it ready for you in class if you need it. Okay, but that's your setup, and that's how you would get your final answer. Okay? Okay, question number 25. Under optimal environmental conditions, a certain bacteria in a sample of milk will double every 42 minutes. A scientist is investigating a sample of 1,000 bacteria. Okay, notice that this one does not have the word continuously in it, so I'm not going to use that PERT formula. Okay? I'm going to go back to my regular exponential growth formula, which looks like this. Y equals AB to the power of X. So my starting value is the 1,000 bacteria that I'm starting with. Now in this one, my growth rate is not given to me as a percentage. A lot of the time it is given as a percentage, but here it's not. It just tells me that I'm doubling. So that means my growth rate is equal to 2, because to double means to multiply by 2. So for B, I'm just putting in 2. And now here's where we want to be careful. Normally we would just say, okay, T minutes, so I'm going to go to the power of T. But that would mean that I was doubling every single minute, and that's not what this question says. This question says that I'm doubling every 42 minutes. Okay, so I want to take that T, which is the total number of minutes, and break it into groups of 42. I want to see how many groups of 42 I'll have in my total number of minutes. And hopefully that sounds to you like division, breaking into groups of 42. So I'm going to take that T and divide by 42. And that'll be the case anytime you have a question like that, where something is happening every so many minutes or every so many years. You'll take that amount of time and divide it by, whatever your segments are. So this is your equation, and that's all question A asks for, is for the equation. So it would be 1,000 times 2 to the power of T over 42. Now question B says use your equation to find out how long it'll take for the population to exceed 3,700. This is going to require a graphing calculator. And again, I apologize, I didn't bring a graphing calculator home with me this weekend. So I don't have one here to demonstrate for you, but I'm going to give you an idea of what to do. I would go in your Y equals. Okay, so hit the Y equals key. And then under Y equals, I'm going to type in my equation. So I would type in 1,000 times 2 to the power, and instead of T, you'll use an X. So X over 42, just like that. And then you're going to go to your table key, which is up above the graph button. You'll have to hit second and graph to get to table. And what you want to look for is you want to look under the Y column and find the first place that the numbers go above 3,700. Okay, so I'll make sure to demonstrate that one in class for those of you who need to see it, but you'll want to look for the first X value where you go above 3,700, and that would be the number of minutes. The other thing you could do with that, and it might take a little bit of doing, but if you didn't have a graphing calculator or you weren't used to using one, you could do a little bit of guess and check here. You could start plugging some numbers in for X and then narrow it down to see when the first place you go above 3,700 was. That might take you a little bit of time, and remember, you are timed on this exam, so my best recommendation is to get used to using a graphing calculator. But if you were in a pinch and you didn't know what to do, you could do that as well. So again, I'll be sure to demonstrate that one and give you a final answer in class. Okay, that's it for this video. The next question will pick up with question number 26. I'm sorry, the next video will pick up with question 26.